Sounds good.
Yeah, hello everyone. Welcome to the Graphics Programming Virtual Meetup. We follow the Berlin Code of Conduct. We have a Discord server. We have a Twitter account, and we also have a YouTube channel. So today's topic is edge avoiding. I really don't want to pronounce this word wrong, but I don't know how to pronounce it. So edge avoiding À-Trous Wavelet Transform for fast global illumination filtering. Let's just pretend that I pronounce it correct. So this is an early paper to apply this edge avoiding À-Trous Wavelet Transform filter for denoising, and the effect is pretty good. As you can see, I apply it to my CUDA path tracer project, where you can see the 1 sample per pixel noise image is like that. And then if we apply the denoising, and we get this pretty good result, even compared to 8,000 sample per pixel reference. But of course, if you look at it closely, then you can see some fine details, especially ambient occlusion, and the shadows get blurred out because this algorithm don't understand those things. So what is the motivation? Obviously, we don't want noise because, well, it just sucks. But also we want to render as fast as possible. And for my CUDA path tracer project, I want it to achieve like interactivity. So if I move the camera without temporal accumulation, then I can probably just have one or two sample per pixel for each frame. And so to make this look nice, we must accept this noisy output is the reality, and then we need some kind of denoiser, which is cheap to make it look nice. The overview of this algorithm, it uses one output buffers and then 2 G buffers, 1 G buffer for the normal and another one for the position. So we have 3 buffers: the ray traced noisy buffer and the normal and the position, and then we put them into this algorithm. We generate a less noisy image, and then we do this algorithm again using this less noisy image as the ray traced buffer. And then we get another image, and so on and so on. I don't know if someone is say something on Discord, maybe not. Let's just mute Discord. And we just continuously using the previous output as input. Those 2 buffers stay the same. We just repeatedly use them. The paper also used optional diffuse buffer to prevent texture details get blurred out. Since I don't have textures in my CUDA path tracer yet, I just don't bother with it. But it can be a good idea to have this another G buffer to just store the diffuse information to prevent textures get blurred out. So how do we actually do filtering? So we want to blur neighboring pixels to make it look smooth. And the filter everyone knows is probably Gaussian filter. We just have like a square neighboring square of pixels, and then we do the weighted average according to the Gaussian curve. This Gaussian filter is good, but also quite expensive, because consider if we have a large filter size, let's say 10 by 10. If we have 10 by 10, then we have 100 pixel to fetch to calculate this weighted average for one individual pixel. And if we have 3 buffers, it's additional 3 times. And this is not nice, since the cost of Gaussian filter just increase quadratically when the filter size increases. And that's how this À-Trous Wavelet filter comes in. So À-Trous means with holes in French. And it's at each iteration we double the filter size. So in the first iteration we have filter size of 5, the next time is 10, the next time is 20, and so on and so on. And we skip more values each time. So you can see in the first level, we use those 5 values to calculate this, to weighted average to get this 1 value. And then for the next iteration, we also fetch 5 values instead of fetch all of those 9 values. This way, we kind of don't have those quadratic explosion problem. Instead, we always have a constant effort per iteration. And so we kind of reduce the algorithm complexity from n squared to n log n. This log comes from we have different levels, and we double the filter size each time. And this À-Trous wavelet, this is just another visualization of the previous algorithm, well, not algorithm, the À-Trous filter, but using in 2 dimensions. We can see the first iteration, we just get all the neighboring 25 pixels. The second iteration, we skip 1 pixel, and then we still fetch 25 pixels. And the third iteration, we also still only fetch 25 pixels. So this is the algorithm À-Trous for like creating À-Trous transform, and then we can construct it and then reconstruct it back. We don't need to actually do reconstruct, because we will actually want to blur the image. So we don't need step 3 and step 5 actually. The only thing we need to do is a convolution, and we're done. So the convolution itself is based on this thing called B3 spline interpolation. I don't know why it is good, but it works pretty nice. And it's just these five numbers, 1/16, 1/4, 3/8, 1/4, and 1/16. It is like Gaussian filter where the center gets the highest weight, and then like other pixels get less and less. The same kind of deal. By the way, for people who don't familiar with the terminology, the convolution, it basically means as we can see from the previous image. For this this pixel, we get the weight 1/16. For this pixel, we get 1/4. For this pixel, we get 3/8. We just have a weighted sum. That's convolution, basically. As a result, it was wavelet transform. We have this blurred image, which is like the Gaussian filter. So it is very similar to the output of Gaussian, but it's faster, so it's pretty good. However, we don't want to blur our edges. Like in the previous image, all the edges get blurred, which still looks nice. So to prevent that, we will apply some edge stopping function. And instead of just doing a normal convolution, we will actually do a weighted convolution. And the bottom term is just we have a normalized factor to make sure we don't multiply something pretty, some large number or small numbers. Our weight of each pixel is calculated by the three terms: the weight of normal buffer, the weight of position buffer, and weight of our ray tracing color buffer. That's how our G buffers actually comes in. The normal buffer and position buffer is used for the edge stopping function. How does it work? So you can see in each individual term, we calculate the differences between our current pixel and the pixel in the convolution that we want to calculate. And so when we calculate the distance, the differences, if the difference is big, then this term will be small. This whole term will be small because it's a negative sign. Which will be we can say it's a large negative number, which means if it's a large negative number, when we do exponential, it will be a very small number. So that means if the normal is close, we will get, if the normal is close, we will get a weight near 1. But when the normal is further and further apart, we will like rapidly decay into, the weight will rapidly decay into 0, and we will get no weight at all. So in practice, it means that only 2 pixels, pixels will only contribute if its normal is very close to the the point of normal we want. So, and also similar position. Position is a similar deal. If the position is further away, then we discard that point's contribution because it is an edge, basically. At each, also those are 3 constants. We choose those constants. It's just 3 sigma number. It's some arbitrary number we choose. At each pass, we decrease the constant of the color buffer by 2. So we kind of allow smaller and smaller variation of colors for larger filters. The heuristic, as I said before, is because if we look at we can consider the contribution of the light at each individual pixel as all the light coming from a sphere. And this sphere is, if those 2 points are really close to each other, their sphere should be, their hemisphere should be very close to each other. So the neighbors, we can use that neighbor sample as the current pixel, and they should give pretty close results. That's why we can kind of by blurring, we kind of get free multi-sampling for free. But however, if there are normal differences, for example, in here, those two places are very close, but they are normal discontinuous, which means we have an edge, and we can't blur this edge. Similarly, if we have a point at here and a point at here, on the screen space is probably really close. However, as we can see, it's actually far apart. So even though the normal of those two places are the same, but the position is further away, we also have an edge. So in those two cases, we can't blur the image. So that's a heuristic for the edge stopping function. And as a result, we get this pretty nice. There are some future works I can do for this project. The first is to compress G-buffers. I can store depth instead of position and just reconstruct position in the filter. That will probably be much cheaper since we will compress the position buffer to depth is like float 3 to 1 float, and much less global memory read to do. I can also do octahedron encoding normals. Since normals are always unit vectors, so it's kind of wasteful to store them normally. No pun intended. And there's a paper for that. I can't remember its name, but you can just search octahedron encoding normal. There should be papers and blog posts for that. Utilizing shared memories, since we do a lot of like G-buffer texture fetch. It's not actual textures, but it's the same kind of deal. We do a lot of global memory read, and neighboring pixels share a lot of those global memory read. So if we can put them into the shared memory, we can greatly reduce the global memory read. That's an optimization I can do. And of course, the last step is just to read and implement better denoising algorithms, because there are a lot of newer research on that, especially those also account for temporal reprojection kind of stuff instead of just in the. So just this algorithm just uses the space dimension, but we can also consider the time dimension. Also, the algorithm don't consider anything about different materials, but more advanced algorithm will probably do something about that. So now it's a demo time. I will show you how it actually looks like, and also show you the code. So yeah, let's stop it here. We can see that if we disable the denoiser, we can see there are a little bit of more fine-grained details when we use higher iterations. But for higher iterations, we need to wait it to finish. If we enable the denoiser, some fine-grained details get blurred out. For higher number of iterations, probably reduce the filter size is a good choice, but by default, I always set it to 10. And This get really interesting when we have one sample per pixel. Since this noisy, like unuseful image, we can get pretty result from it. It still looks a little bit dirty, but it is much better than the noisy output we got before. And yeah, also I can show you the code. So first we have this denoise function. Those are just a bunch of CUDA boilerplate. The important thing is this for loop, where we have the input position buffer, normal buffer, and color buffer, which is like the path trace output in the color buffer. We call this denoising, for each iteration, we call this denoising kernel with like bigger and bigger step widths. The first time is 1, second time is 2, etc., etc. And the interesting thing is here I'm doing buffer ping-ponging, but I don't want to change the color buffer, so I do these tricks like this. I change the back buffer and front buffer, but also I change the color buffer into the back buffer. This way, the first time I will use color buffer as input, the second time is the back buffer. The third time will actually be the front buffer, and the color buffer will only be used for the first time. So this is what this trick is doing here. And for the denoising kernel itself, I basically copy and paste the code from the appendix of the paper. They provide full GLSL code. And you can see here is just a loop to do convolution, and it's always fixed size. It's -2 and to 2, so it's 25 by 25. Sorry, 5 by 5. So it's 25. So it's 25 iterations inside this loop, and for each individual loop, we calculate this edge avoiding function using the formula we already saw. You can see the exponential here. And then we just do the weighted sum, and also we have a normalization term, and at the end we just use sum divided by the normalization term to get the result. It is a pretty persistent theme in the computer graphics algorithm to have this kind of normalization term, so it should be familiar for people, for at least some people. Any questions before I end this?
This might be more of like a GPU programming question, but I'm curious. So it looks like you are still going to do the calculation with when it's like the weight makes it basically 0. So not really contributing at all because you're like on an edge or something, but you're still going to do the calculations. So would it be better to like exit out early, or is it the problem that like you need everything to do the same amount of work? Or?
Yeah, it shouldn't help. That's well, it won't hurt, but it won't help. At least I think, because if you exit early, it's a divergence, right?
Yeah, that's true. Is it better than doing a texture read?
You just waste cycles basically, so it won't help.
Are you doing the texture reads? Yeah, like if could that slow it down if you're still like reading in the normal buffer position?
Yeah,
buffer?
those 3 will be slow because those 3 are global memories, right?
Yeah, so maybe it'd be better to exit out before you get those.
Maybe
that's probably
put
just
them in the shared memory. Yeah.
Yeah. Okay.
Any other questions? Okay. I think we can end it here. And yeah, we can discuss it after I end the recording. Yes.